Hi everyone, welcome back to my channel. So in today's video we are going to discuss about assertions in system Verilog at one go. So I have already made a bunch of videos on assertions. I have made a separate playlist for that. I'll link that in the description box. If you want in detail explanation about assertions, you can go there and check it out. But if you want to have the entire concept in assertions in one go, maybe this video is helpful for you. Hope you like this video, and if you like it, please do give it a like and share it to all the VLSI aspirants. Before entering into this video, if you are new to this channel, consider subscribing my channel and hit on the notification bell also. Also, you can join me in my Telegram channel in order to get the courseware related to Verilog system, Verilog and UVM. And you can follow me on LinkedIn in order to get updates related to design and verification domain. What are assertions and why what are the advantages of assertions? Why do we need assertions? So all these things before entering into what are different types of assertions in system Verilog, right? So if you are new to this channel, consider subscribing my channel and hit on the notification bell also. Also follow me on LinkedIn and also Instagram, and you can also join my Telegram channel where I'll be uploading latest news related to VLSI and also opportunities or vacancies that I encounter in my LinkedIn channel, right? So yes, now getting into today's video, right? Assertions. So, what are these assertions? Basically, in verification, we will be writing checkers. Okay, I have already explained clearly about Verilog test bench architecture code in system Verilog. I'll link that in the description box. You can go there and check it out. There we have already explained clearly that scoreboard. In scoreboard, what you will be doing, you will be comparing the expected output to the actual output. So basically this comparison is nothing but we will be writing it in the form of checkers. Okay, so checker is nothing but it is used in order to check the functionality of the design. Basically, as I told you, it will be checking in the checkers. What you will be doing is you will be writing the output. You will be checking whether the output that your design is producing is equal to the expected actual output. Like for example, when you have written when you are reading some spec, it will be clearly mentioning what kind of output that particular design has to produce. So that output is called the actual output. And when you are verifying, when you are sending some series of inputs to your DUT like RTL code, it will be giving some outputs, is it or not? So those are the expected outputs. So in scoreboard you will be writing checkers where this actual output and expected output will be compared. Okay, so if the actual output and expected output are same, then our particular code or particular design is in a correct is working correctly. So what is all this? Here we are just checking the functionality of the design. Okay, so many of them say that assertions and checkers are same, but no, there is a difference between this assertion and checkers. As I told you before, checkers are used in order to compare the actual output and the expected output. So what you are doing here, you are just checking the functionality of the output. Okay, functionality of the design, whether the design is functioning correctly or not, whether the design is taking the input and giving the output in a correct manner or not. So that you are checking in case of checkers. But assertions is different. Why is it? Because when you are writing an assertion, you are writing in such a manner that it is checking the behavior of the design, like how the design is behaving when you are giving series of inputs, how the design is behaving for those series of inputs, that you will be checking in case of assertions. Okay, hope you got an idea on what is the difference between checker and assertion. So basically checker is used to verify the functionality of the design, whereas assertions are used to verify the behavior of the design. Okay, now let me tell you a small example with this so that you can know the difference between these two things. Okay, for example, let us consider we are just reading some spec, and that spec mentions that our output should toggle for every two clock cycles of valid input. Okay, that means for every two valid inputs. For example, if there are two valid inputs in the continuous two clock cycles, then in the third clock cycle, the output should toggle. So this is the thing that spec designs, that the spec mentions. Okay, but when you are writing the checker, it will just check whether the output is behave, whether the output is actual output and expected output are equal or not. That's it. But when you want to add this particular functionality, like when you want to add this particular thing, like the output for every two valid inputs of clock cycles, the output should toggle. So this is the behavior. For every two inputs, the output should toggle. So this is how the output should behave. So this is the behavior for that particular design. Now how you are going to do it? You are going to do it with the help of assertions. So in these cases, basically you will be using the assertions. You will be writing the assertions. Okay, you will be writing the assertion that for every continuous two clock cycles of valid input, the output should toggle. So in this way, you will be writing the assertion, and based on that assertion, the particular design will be behaving. So hope you got the difference between the assertions and checkers. Basically, many of them will say that assertions and checkers are same. Yes, they are same in some way, but this is the minute difference between checkers and assertions. Okay, so as there are various advantages in using assertions. Let us see those advantages one by one. Basically, in verification methods, as I already told you, assertions are very important because they are having many advantages. Like, for example, assertions helps to capture the improper behavior of the design. Okay, so basically, when there is any improper behavior in the design, assertions are used in order to easily check those things. Why? Because basically, okay, as a here if you see, it improves debugging time, it is said that. So why it improves debugging time? Okay, so basically, as I told you, for every assertion, we'll be writing assertions for a group of signals. Is it or not? So basically, when there is an assertion failure, then you can directly point out that particular signal instead of checking where the signal has actually gone wrong. Is it or not? Instead of checking a bunch of signals, if there is one assertion failure, then you can point out that particular signal, and we can check that only one on that signal where that particular signal has gone wrong. So this in this way, since we are among the bunch of signals, since we are pointing out only one particular signal, so that the debugging time will be very reduced when you are writing assertions. Okay, so in this way it will be easy, in order to it will improve the debugging time, and also it will be checking the design specifications and report errors. Okay, so for every based on the spec, we for the design we will be writing some assertions, and then with that assertions you can check whether there are any errors or warnings in that particular signal. Okay, so and also many other advantages, like it can be reused across various verification test benches, and it can also be parameterized. And also one more advantage is that we can easily turn on or off these assertions based on our requirement. For example, if you don't want that assertion for some particular point of time, then we can just turn off the signal, and or else turn off that assertion, and we can easily turn on the assertion, just like we have done for constraints and randomization. We'll be enabling and disabling these assertions also. Assertions are used in various other languages, like Open Veras, or in assertions in Specmans, and property specification languages. Like these are various languages where you can find assertions also. System Verilog assertions are called as SVA, which is SV based assertions. Okay, so what is the advantage of this SV based assertions means, by clubbing all the advantages of other languages assertions, these SV assertions were built, because so that SV assertions are the best among all the assertions that you use in various other languages. And also one more advantage of these assertions is that we can add these assertions in both test bench as well as design directly. Okay, we don't need any other interface in order to combine this test bench and Verilog for assertions. Okay, for assertions you don't need any other special interface. You can write it directly in design as well as you can initiate directly it in test bench also. And also SV assertions are very easy to learn and implement. Okay, and one more thing is essay assertions can be reused in both functional and formal assertions. So basically, we will be using in SV in our system Verilog, we will be using functional assertions. So functional assertion means in order to check the functionality and behavior of the design, we will be developing this assertions in system Verilog. So basically, in system Verilog, there are two kinds of assertions. One is immediate assertion, and another is concurrent assertion. Okay, so we'll be seeing what is this immediate assertion and what is this concurrent assertion, and what are how we are going to write assertions in immediate, how we are going to write assertions in concurrent assertions. So we are going to see all those things. Firstly, let us see what is immediate assertion and what is concurrent assertion. So from the name itself, you can say that in assertion, if the condition is checked at the current simulation time, at that particular time itself, if the particular assertion that you have written is checked, then that is called as immediate assertion. Basically, immediate assertion is very similar to if else conditions. Okay, so basically when you are writing the if else condition, how you will be checking, how it will be checking, if else block will be executed in the active region itself. So basically, how the if else condition execution will be done, if there is, if condition is true, then else condition is false, if condition is false, then else condition will be true. So immediately it will be checked. Similarly, immediate assertion is also checked at that current simulation time itself. Okay, now coming to concurrent assertions. So basically from the name itself, you could say that if there are sequence of assertions which are spread over multiple clock cycles. So basically, sequence of assertions means not single assertion. So a group of assertions. So since a group of assertions will be having multiple clock cycles, when you want to check all this group of assertions, then we call that as concurrent assertion. So here the checking won't be done at that current simulation time, because here there are group of assertions and one is tied to another. So that is why what you will do, you will be checking it in a sequence manner. So that is why those are called as concurrent assertions, right? So these are the two assertions which we will be finding in the system Verilog. And in the upcoming sessions, we will be talking about what are immediate assertions and what are the concurrent assertions, like what is SVA checkers. Checkers also we will be seeing, and also sequences, everything we are going to see about. There, see, if you see here, there are various ways in order to write your assertions, by using implication operators, by using overlapped implication operators, so everything. So we'll be checking all these things as they are having again. System log assertions are also having methods like dollar $rows, dollar $file, dollar stable, dollar past, everything. So we will be discussing all these things in the upcoming sessions. I'll be making a series of videos on this system log assertions. So please don't miss all these sessions on assertions, because as I already told you, assertions are really important in system Verilog, right? So that is all for today. Thank you all. So basically, as I already told you previously, immediate assertion is nothing but it is just a form of if else statement. Okay, so if you see here, this is the syntax of immediate assertion. Assert, okay, whatever expression you want to write, you can write. Like for example, you are writing as A and B. Okay, this is my expression, and the past statement, if it is not passed, then else fail. Okay, so this is how the assertion, you will be writing the assertion, which is called as immediate assertion. Okay, here if you see, if the expression is evaluated as true, then the past statement is executed. If the expression is not evaluated, then what happens, the fail statement will be shown. That means there is an assertion failure. Fail statement is shown is nothing but there is assertion failure. So assertion failure means then you can know at what point of time this particular signal is being failed. Okay, this is why we use assertions basically, in order to reduce our debug time, because when you are designing the complex circuits, it is not easy for you to check each and every signal in order to know where the actual bug has occurred. Which is why when you are writing assertions, then you can understand that, for example, if you are writing an assertion for these two signals A and B, and if there is an assertion failure, then you can immediately find, okay, there may be bug in either this or this signal. Okay, then you can limit your um, debugging time to only these two signals, which is why assertions are really important, right? Hope you got it. So if an assertion evaluates true, pass. If it is failed, then it is assertion failure. Okay, so if there is any assertion failure, basically past statements, if it is passed, then it will be executed, everything will be fine. If it is failed, then it will be showing you there is an assertion failure. Is it or not? So basically, when you are writing these fail statements, when you are building this assertion, now depending upon the failing statement severity, it is again, there are again four categories within the assertion failures. Okay, dollar fetter, dollar error, dollar warning, and dollar info. Okay, just like you'll be seeing in your log file, you'll be seeing dollar error, like you'll be seeing sometimes errors, sometimes you'll be seeing warnings. Okay, similarly sometimes you'll be seeing the fatal errors. Okay, and sometimes you'll be seeing the dollar info. So basically these are nothing but the severity levels of your error. If there is any runtime error, then it will be shown as dollar fatal or dollar error. Okay, if there is any just runtime warning, there is a, just if it is basically warning means it will be it can be suppressed by using some tool specific manners. Okay, and if there is any dollar info, basically if there are nothing much specific about that particular error, okay, then basically it will be showing you in the format of dollar info. Okay, so this is how these are just the severity levels of the error that is caused during this um, immediate assertion, right? So this is about the immediate assertion. So let us see how we are going to write the assertion, immediate assertion. Okay, for example, if this is my particular code, okay, so here I am having clock A and B. These two are inputs, clock and A are inputs. Okay, now AB, for example, clock for every here if you have generated the clock, always hash 5 clock equal to negation of 5, negation of clock. That means now the clock period is total of 10 time units, right? Now initial begin, I'm just passing the values to A and B. So A and B are 1 and 1, and then after 15 time seconds I have changed the value of B to 0. Since I didn't change the value of A, it will be 1 only. And after 10 time units it is 1, and I have changed the A to 0. And after 20 time units it is 1. And then after 10 time units I have completed my entire passing values and ended. Okay, now for this particular spec, if there is some rule for there is some condition that for every passage of clock assert A and B, that means for every positive, now if you are writing the assertion in this manner, what is the meaning of this? Always at the rate of passage of clock, that means for every passage of clock assert A and B. That means what happens if A and B both are 1, then this assertion occurs. That means assertion is passed. If A and B is not 1, then the assertion is failure. Okay, in order to know whether A and B signals are 1. Okay, because basically 1 and 1 means you will get the output as 1. Is it or not? And condition. So you don't want this to be failed. Like 1 and 1. You need the output as 1. So now what happens? If there is assertion, any assertion failure, then at that particular clock time you can just check that whether A has become 0 or B has become 0 instead of checking the entire clock cycles. Okay, now let us see here assert A and B. So if you see here, for every passage of clock the assertion checking will be done, right? So now if you see here, for every passage of clock A is 1, right, here B is 1. So since A is 1, B is 1, assertion has passed. Fine. Now after this, again here this is negation of clock, so there won't be any checking done, assertion done. So again the assertion is checked here at passage of clock. Now at this passage of clock A is 1, but if you see here B is 0 because it is reduced, so the assertion is failed. Again next passage of clock it will be checking A is 1, but sorry, A is 0 but B is 1, but A is 0 and B is 1, so assertion is failed because assertion needs to be A and A both should be 1. Now again at passage of clock 0 1, so again assertion has failed. Okay, now at this point where A is 1 and B is 1, so assertion has passed. Now what happens? You have to check in these three clock cycles, because these three clock cycles you will be telling that assertion has failed. Okay, at 15 nanoseconds you have to check, at 25 nanoseconds you have to check, and at 35 nanoseconds. Now what happens? The debugging time has reduced from this entire clock cycle to these three clock cycles just by writing a single line which is an assertion. Okay, this is how the assertions are useful. So this is how you write an immediate assertion. Immediate assertion means just when you want to write a condition, and that particular current simulation time only the assertion will be checked. Okay, this is how you will be developing your immediate assertion. Now coming to concurrent assertions. Okay, so concurrent assertions means basically these assertions are evaluated over a period of time. Okay, like basically if it will be taking multiple clock cycles in order to evaluate these concurrent assertions. So, and you already know that, like when we are talking about the SV regions, I have already told about this assertions. Okay, you can just check that SV regions, like schedule semantics. Okay, I link that in the description box, or I link it in the title of this box. Okay, so you can title of this window, you can go there and check it out. There I have particularly mentioned that concurrent assertions are sampled in the preponed region, and they will be executed or evaluated in the observed region. Is it or not? So, these are the concurrent assertions that we are talking about. Basically, as I already told you, immediate assertions means they will be executed as soon in the active region itself, as immediate at a simulation time, at runtime itself they will be executed. But concurrent assertions are not like that. They are executed over a period of time. What is that period of time? That is, they are sampled in the preponed region and they are evaluated in the observed region. So it takes a period of time in order to evaluate these concurrent assertions. Okay, and also one important thing about this concurrent assertion is that concurrent assertion is evaluated only for every clock tick. Okay, so for every positive or negative that you are giving, they will be executed. Okay, so that is why we call this concurrent assertions are clock based evaluation model, because they will be executed only based on the clock. So that is why concurrent assertion is always tied to a clock definition, right? And as we already discussed, these are sampled in preponed and evaluated in the observed region. Okay, and if there is any pass or fail statements, they will be produced in the reactive region. Right, so this is about the concurrent region. This is most frequently asked in interviews, like concurrent assertions where they are sampled and where they are evaluated and where the pass or fail statements will be executed. Right, now concurrent assertions can be declared in, as you already know, assertions. In the previous session, I have told you can write assertions in both RTL as well as test bench. Similarly, you can declare these concurrent assertions in always blocks, initial blocks, and you can write it in either interface or program or module block, program block. In everywhere, you can insert this concurrent assertions. Okay, here in the immediate assertions, we have already talked that when you want to assert is the keyword here. Okay, assert means what happens, the execution takes place, the execution of this assertion takes place by using the keyword assert. Similarly, in this particular concurrent assertion, you will be using the assert property is the keyword. Okay, you will be using assert property. So we will be discussing about what is this property and all in the upcoming sessions, right? So this is the assert keyword. Along with, if there is a assert keyword along with property, then you can declare that as concurrent assertion. This is how you can differentiate basically. Just a simple what I can say tip for you. Generally, if you see as assert property, assert property, then that means it is a concurrent assertion. If there is no if there is only assert and the logic, then it is a immediate assertion. Clear? So this is how basically a tip in order to differentiate between immediate and concurrent assertion. Now let us see how what is the syntax of this concurrent assertion, because as I already told you, concurrent assertion is executed over a period of time, and also in immediate assertion you are having only one, basically one logic or one sequence. But in concurrent assertion it is not like that. You will be having multiple sequences in case of concurrent assertion. So let us see how we are going to develop them. Right? So if you see here, For example, you are having just only one logic. Okay, you are having only one condition. Logic is not, that is condition basically. Okay, so if you are having only one condition, then how we are going to do it? Assert property at the rate of passage of clock, request 1 or request 2. Now what happens? You are telling it as assert property, as I already told you, so it is a concurrent assertion. So what is the logic here? What is the condition here? For every positive edge of clock, either request 1 or request 2 should be high. Okay, so in this way, 0 0 1 1 1 0 0 1, at least, since it is or, so at least request 1 or request 2 should be high. So this is how I am writing if there is only one condition. Okay, now what happens? For every of these three conditions, for every of these three things, the assertion will be passed. If both request 1 and request 0 are 0, then the assertion is failed. Okay, so this is the condition for this particular assertion. Okay, as I told you, if there is more than one condition, then how we are going to do it? What if it is a complex property? If this is only single line, if there is only single condition, then it is a basic property. If there are more number of properties, then what happens? That is called as complex property. Okay, before seeing what is this complex property and all, okay, let me give you a small introduction on what is this property and all in this concurrent assertion. So basically, in concurrent assertions, one is sequence and another is property. Okay, you have to remember these two things in this concurrent assertions. So what is the sequence and what is the property? So basically, sequence is nothing but, okay, if you say, I'll just explain this with an example to you so that it will be clearly understood for you, like what is sequence and what is property and what is the difference between these two things. Okay, so if you see here, sequence and the name of the sequence, this can be any name. Okay, I'm just keeping the sequence name as request sequence. So this is the name of my sequence. Basically, when you are writing a assertion in concurrent assertions, how you will be write sequence and sequence name. So this is the syntax and the condition. So what is the condition here? Request signal hash hash 1 grant signal. What does that mean? So in this sequence, first defining that the request signal should be coming first. This is the first event. Okay, so after this event, then after one time unit of delay, that means after one clock cycle, the grant signal should be followed. Okay, so this is the meaning of this particular sequence. Okay, so in this sequence I am having two events, which is request signal and grant signal. Here after request event is done, after one clock cycle, grant event should be followed by the request signal. Okay, and then the end sequence. Okay, so this is my sequence. Now what I am doing? Okay, I am just, in order to, as I already told you, in concurrent assertion you will be asserting property. So what I am doing, I am making this property. What here in this concurrent assertion you can have many number of sequences. So this is one sequence. In this way you can have two or three number of sequences also. Now in property what you will be doing, you will be combining all these sequences and you will be writing the property, and then at a time you will be asserting property. So now what happens, instead of asserting all these sequences one by one, you are combining them in the property. Either if there is one signal or if one sequence or many number of sequences also, you will be making that as a property and then you will be asserting the property. Clear? This is the concurrent assertion. Now what happens? Property handshake. So at the rate of passage of clock, okay, request sequence and then grant signal. Now what happens? This is the implication operator. You will be seeing, I'll be explaining about what is this one, what is this one in the upcoming sessions. Don't worry about that. So now coming to this property handshake, what happens for every passage? So property handshake means this is also name. Okay, just like sequence and any name you like, and similarly property and any name. Okay, this property name is handshake. Now for every passage of clock, so this is my sequence. Request sequence should be followed by grand signal. Now what happens? So this is my sequence. Similarly, for example, if you are having two sequences, so this is my one first sequence, which is sequence request sequence. Similarly, I can have another sequence like request name. Okay, I'm having another condition here. Right now, what happens? Request, I can just write it as request sequence should be followed with name sequence. Okay, so now what happens? This logic will be followed by this logic. Clear? In this way, you can combine all the sequences within the property and then end property. Just like you will be when you are writing a sequences, it should be starting with sequence and it should be ended with end sequence. Similarly, for property, it should be followed by property keyword and end property. Okay, now what you will doing, you are writing the sequence and you are writing the property, and then you will be asserting the property. Asserting the property is nothing but execution of this particular assertion. Okay, so execute this particular handshake. Now what happens? This handshake is consisting of request sequence name. So inbuiltly what will be happening, this name and this request sequence will be asserted. That means the logics behind these two will be asserted. Clear? So this is the how you will be writing the concurrent assertion. So let me give, if you don't understand this particular thing, let me explain you much more easily in a theoretical way, so that when we'll be explaining the code on this particular concurrent assertion in the upcoming sessions, you can easily understand. So as I told you, SV assertions of this concurrent assertions, basically when you are because immediate assertion means there will be basically only one sequence and it will be executed, but concurrent assertions, as I told you, is very important because immediate assertions there won't be. Basically, when you are writing assertions, you will be mostly using this concurrent assertions itself. Immediate assertions, basically when you are just writing some basic conditions only, you will be using that immediate assertions. So concurrent assertions are very important when it comes to assertions. So just before we have explained, right, in this I am just explaining the steps like how we are going to write a concurrent assertion. First you will be creating the boolean expression. Boolean expression is nothing but, for example, if you see here, okay, see, uh, at the rate of passage of clock a equal to 1, so this is my boolean expression. In this way, first you will be creating all the boolean expressions using the operators or using the yeah, you'll be having events, multiple logical events. So using all these things, you'll be creating the boolean expressions. Like boolean expression is nothing but basically depending on the, for example, if you want to check on these two signals, so what you'll do, you can use either and symbol or symbol, just we have done in the previous examples. Okay, first you will be creating the boolean expression. Now what happens after you have decided which boolean expression you have to apply on these two particular signals or something, then you will be creating the sequence for those expressions. So how do you create the sequence? By using the sequence and end sequence. So within the sequence you will be writing the name of the sequence and then the logic here. That means what happens here, you will be writing this particular logic, that is here, see, at the rate of passage of clock a equal to 1. So this is the as a sequence, this is the thing that will be here in this particular logic. Okay, so now what happens, in this way you can have either single sequence or many number of sequences. Okay, basically if there is only one sequence, then you will be writing only one sequence and ending. In this way, if you are having some two or three sequences, you will be writing two three sequences similarly in a manner. Okay, now what happens, now you will be creating the property. So creating the property means number of sequences can be combined logically or sequentially to create more complex sequences. Why is it? Because if there is only one single sequence, then it is fine. If there are two or three sequences, then it will become complex in nature. Is it or not? So now what happens, in order to make all those complex sequences in a easy manner, you will be combining all these complex sequences in a property. So here you will be using property and end property in order to mention the property things. Here what you will be doing, you will be using all the expressions or sequence expressions, or if you want to test which type of expression you want to test, you will be testing or writing all these expressions within this property. Now what happens after creating the property, you will be asserting the property. Asserting the property is nothing but now it is verified. Okay, the property is the one that is verified during simulation. It has to be asserted to take effect during simulation. Clear? Okay, you will be using the assert keyword, assert property and property name. So this is the property name. That is what I have explained here. Okay, so these are the four things you have to do when you are writing a concurrent assertion. First, you will be creating the Boolean expression, you will be writing the sequence, and then you will be creating the property where you will be inserting the sequence expressions, and then you will be asserting where you will be asserting this particular property with this property name. Okay, clear? Now coming to how to develop a system Verilog assertion sequence. Right. So in concurrent assertions, we have already discussed that we can have any number of sequences, like we can have 3 or 4 number of sequences also. And what we will be doing, instead of asserting all these individually, we will be combining all these assertions into a property, and then we will just assert that property, so that all the sequences within this property will also be asserted. Right. First thing here, sequence. Okay, sequence should be followed by sequence name, which is sequence now. Now here, what is the condition that I am writing? At the rate of passage of clock, a equal to 1, double equal to 1. So that means for every positive edge of the clock, what is the meaning of this assertion? So if you want that particular input like a want to be if you want that to be high for every passage of clock, then you should be giving it in this format, so that it will be checking that whether a is continuously 1 for all the positive edges of clock. And if at any point of time, if a value has become to 0, that means if a is low, then at that point of time the assertion will be showing you as a failure. At that time sequence, it is showing that the assertion is failed. So what can you do? You can just check that assertion, and based on the time slot that it is given, you can go there and check it out why that a value has become too low at that particular point of time. Right. So in this way you can check the debugs easily by using the assertion. So this is how you will be writing if you want particular input to be high for every passage of clock. Right. Now if you have two inputs, okay, and if you want to check if you have a condition like that either of these inputs should not be both the inputs should not be low, at least one input should be high, so that that particular logic will be happening. So how we are going to write that? See, at the rate of passage of clock, a or b, this means either a or b should be high for every passage of clock. Okay, if both of these are low, then the assertion happens to be failed. Got it? So if you want both the inputs to be high, then what you'll do, instead of or, you'll be keeping AND operator, so that what happens, for every passage of clock both A and B should be high. If both A and B are not high, then what happens, the assertion will be failed. Okay, in this way the assertion will be happening. Right. If either of A or B is high, if both signals are low, then the assertion will fail. Got it? Now, for the same thing, for example, this is how you will be using the logical operators here, a sequence with the logical relationship, like or operator, and operator, negation. So all this you can do it. Right. Now sequence with timing relationships. This is really important. So basically, you are having a logic that, for example, you are having two inputs A and B, and after A is high, then after one clock cycle the B should be high. Okay, so this is your logic. So how are you going to mention it? Okay, you got my point. A should be high, and after A is high, then after next clock cycle the B should be high. So this is how you should be designing. This is how you should check your design. Then how we are going to write it as an assertion? A hash hash 1 of B. That means what happens? Hash hash means it's a delay symbol. Okay, you already know that hash is nothing but a delay symbol. So in assertions you will be using double hash in order to show the clock delay. Okay, so what happens? First, after A is high, hash hash 1. That means after one clock cycle, B will be high. Now, if you see here, hash hash 2. That means after A is high, then after two clock cycles, B will be high. Got my point? See, the sequence checks for signal A being high on a given positive edge. For every positive of clock, it will check whether A is high or not. If A is not high, then it doesn't check the B condition. But if A is high, then what happens? If A is not high, then the sequence fails obviously, because since A is not high, the assertion is failed. So what is the condition here? If A is high, then after two clock cycles, B should be high. So this is my condition. And now if A is high on any positive cycle, the signal B should be high for two clock cycles after that. That means for first clock cycle, if A is high, then after two clock cycles, the B should be high. So this is the condition. If this condition is, that means after two clock cycles, if B is not high, then the assertion fails. Got my point? Yes, so this is clear. So this is how you will be checking the assertions. So clock delays are in this way, like hash hash represents the clock delay or cycle delay. So for how many clock cycles you want to take delay, it will be giving it as a number, like hash hash 1. That means one clock cycle. 2 clock cycles, right? So if it's hash hash 0 means both should happen. For example, if you want that to happen both at the same time, then you will be giving it as A hash hash 0 B. That means as soon as A is high, the B should be high in that same clock cycle itself. Clear? So again, you can give it as a range also. Like you can give, for example, if you are giving it as 4 to 6, then what happens? Between 4, after A is high, between 4 to 6 clock cycles, the B should be high. Clear? So this is how you will be mentioning it, the clock delays. Clear? Yes. So if you see the example here, hash hash 0 means there should be no delay. Expression on LHS and RHS should hold true at the same time. Okay, that means both should be true at the same time. If it is hash hash 1, that means after a particular expression in RHS is completed, then the LHS thing should be taking place. Clear? Now 2 to 4, that means within the range. That means after first thing is checked, then within 2 to 4 clock cycles, the second thing should be high, or second input should be high. Clear? Yes. So in this way again, if you want the same thing to happen for some 4 or 5 clock cycles, then how can you do? There are repetition operators within assertions. So let us see how we are going to use this repetition operators. So if you see here, sequence within the sequence and unsequence, for every passage of clock, okay, request 1 hash hash 1 request 2. So just check these, only this thing. What happens now? So as soon as the request 1 is high, after one clock cycle delay, the request should be high. Clear? So this is the condition. But the same thing should happen for three number of times. That means after request 1 is high, then for continuous 3 clock cycles, the request 2 should be high. Clear? If any of this condition fails, the assertion will be failing. That means after, for example, if you are taking it as this is my clock, okay, this is my clock, and this is my request, okay, 1, and this is my request 2. Now what happens here? The request 1 is high at first clock cycle. Now what happens after request 1 is high for the first clock cycle, the request 2 should be high for the next clock cycle. Okay, this is second, third, 4, 5, 6 clock cycles for every positive clock, right? So for the next positive clock, the request 2 should be high, and again for the second time also it should be high, for the second clock cycle also, for the third clock cycle also it should be high. If within these three clock cycles, if any, for example, if for these two clock cycles if it is high, and for the next clock cycle if it is low, then the assertion fails. Okay, that means it should be continuously high for the next three consecutive clock cycles. So that is what meant by this particular logic. Okay, request 1 hash hash 1 request 2, within the square brackets you are giving it for three times. That means continuously it should be high for three consecutive clock cycles. Clear? Now either you can write it in this way easily, or you can just give it as like this. If you see, instead of this you can write it as request 1 hash hash 1 request 2 hash hash 1 request 2 hash hash. That means total of 1, 2, 3. So instead of giving this, you can just give it in this manner also. Clear? Now, the same thing, like if you see here, three consecutive clock cycles. Now you can give it in range also. Now if you see here, request 1 will be high, then request 2 should be high within 2 to 4 clock cycles. That means you are giving the range. Okay, so it must be true. It must be true for minimum 2 and maximum of 4 clock cycles. That means either 2 clock cycles it should be high, or continuously 4. Within 2, 3, 4 clock cycles, at least it should be high for 2 clock cycles, and maximum it can be high for 4 clock cycles. Clear? So this is the range I am giving. That means within 2 to 4, between 2 to 4 clock cycles, it can be high for any number of cycles. But it should not be, if it is only one clock cycle high, then the assertion is failed. If it is for 5 clock cycles or 5 high also, the assertion will be failed. Only it should be between 2, 3 and 4. So this is the range. Okay. For example, here, as I told you, you want it to be high for continuous 3 consecutive cycles. Now, if there is a condition that it should be high, but there is no mandatory that it should be continuous, then how can you write, instead of the star symbol, you can just mention equal to symbol. That means here, if you see, the request 1 is high and the request 2 will be high for the next 4 clock cycles, but it may not be continuous. That means after 3 clock cycles it can be high, and then after 2, and then after 1 it can be high. But after request 1 is high, for at least 4 times the request 2 should be high. Okay, but it is not mandatory that they should be consecutive. Clear? So this is the condition for in this manner. In these many ways you can write the assertions based on the logic and based on the condition that you are writing on that particular input. You will be using all these ways in order to write the thing. Now the same thing here, if you see, these star indicates that they are consecutive. Then that means here, if you see, the same here is consecutive 3 clock cycles consecutively, either 2 times or 3 times or 4 times, it should be high. Similarly, here if equal to means it should be high for 4 clock cycles, but it is not mandatory, they are continuous. Similar thing this for this also within the range. That means it can be high for either 2 clock cycles or for 3 clock cycles or 4 clock cycles. But they need not be all consecutive in nature. Clear? So this is how you will be writing the sequence. Now, as I told you, if you are having only one sequence, you can directly mention the clock within the sequence itself. Like at the rate of passage of clock, you can directly mention the clock within the sequence, and you can directly assert the sequence itself. But if you are having more number of sequences, as I told you, you will be compiling all those things in a property, and then you will be asserting the property. So how we are going to do it? So if you see here, this is my sequence. Similarly, if you are having some 2 or 3 for one sequence also, you can do it. There is no problem. So I didn't mention any passage of clock because I have just written the logic. So what is the logic? A hash hash star to B. That means after A is high, then the B should be high for next clock. So after 2 clock cycles, the B should be high. Okay, so this is the logic. So based on this logic, I am asserting the property by using implicating this within the property. So here property P at the rate of passage of clock sequence. So what is the sequence? The sequence is A hash hash star to B. So instead of writing all this thing, you can just mention the sequence name. Okay, and similarly, if you are having two sequences and if you want to check that condition also here at the rate of passage of clock, you can just mention it like that, and then you can assert the property. Okay, you can either write this in this way, or if you are having only one sequence, then you can just initiate the clock within the sequence itself. So this is one way and this is another way. You can do any ways based on the number of sequences you are having, right? So and then the next thing is implication operator. So before going into implication operator, let me show you, since we have already discussed about the sequences and properties. Okay, since we have seen all these repetition operators and all within the sequences, let us do one example on these assertions before going into the implication operators, right? So Yeah, let us see the example here before going into the implication operator. So if you see the assertion program here, okay, module assertion, here I am taking clock as inputs and two inputs which are request 1 and request 2, REQ1, REQ2. So always I have generated the clock, always at the rate hash 2 is the clock cycle. Total time period of clock is 4 time units, okay. Clock will be negate of clock for every 2 clock cycles, for every 2 units of time, right? And then I am writing sequence. So I am having only one sequence here. As I told you, you can have one sequence or more number of sequences also. So what is the sequence here? Request 1 star 2 hash 2 request 2. That means after request 1 is high, then after 2 clock cycles request 2 should be high. So this is my condition. Now I want to assert this condition. What I want to do here, I am just initiating the property. So within property I am writing that at the rate of passage of clock. For every passage of clock, this condition needs to be checked. What is the condition that needs to be checked? Request 1 star 2 request 2 needs to be checked. So I'm writing it in the property. And then I have ended the property and then I'm asserting the property. So this is the way how you will assert. Okay. So assert property of prop. So what is the prop? Prop is nothing but the name of the property. So I'm asserting this property, okay. And then in order to see the waveforms you will be writing this dump file, okay. In order to see the waveform on the EDA playground, you will be using this dump file thing. Presently I'm not able to open the waveform due to some net issues, so I'll be explaining that in the some other video by showing the waveform. But as for today I'll be just showing you how the assertion fails on the log file itself, okay. Don't worry, it will be clear for you, okay. So now I'm just giving the input values. I'm just doing the input values. Like if you see here, first initially at 0 time delay I'm just giving the values as 0 and 0, and then based on the time delay, see, for 4 time units I have made request 1, and then since I didn't give any time delay here, again this also be request 2 also be 1 will for hash 4 only. Next hash 6 request 1 is 0, request 2 is 0, hash 10 request 1 is 0, hash 20 request 2 is. In this way I'm just throwing some values and then I'm finishing it and then I'm ending the module. Now if you see here, this is my condition. So now I want to check where the assertion is being failed, okay. So now if you run this particular property, you will be seen where the assertions are being failed. So from this you can check where the assertions are failed and then you can check the that particular time point where the assertion is being failed and you can do it. So let me run it and show you. Let us see where the assertions are being failed. So see, here if you see at 2 nanoseconds the assertion is failed. Okay, and then at 18, at 22 nanoseconds, at 26 nanoseconds. So these are the time slots where the assertions are being failed. And in the remaining thing, in the remaining places, the assertions are passed. So let us do one thing here. Let us see this one. See what I have done here is, here after request 1, after 2 clock cycles, the request 2 should be followed. Okay, so this is the assertion that I have done. So for that case, what I have given here, after 4, I have given 6. So it is having 2 nanoseconds of time where both are high. Okay, so because since I have given this, I have the request is the assertion is failed after 18 nanoseconds. Now, for example, if I remove this particular 6 time seconds and if I run this code, what is going to happen? Okay, so the condition like 4 after 4, here it is again the request to is 1 for again 4 nanoseconds only, but it's not 2 nanoseconds. That means there is no 2 time clock cycles of time delay. So which is why if you see here at 14 nanoseconds also the session is failed. Okay, for example, if you are not if you are keeping this as hash 6 and if you run this code, what will happen at 14 nanoseconds? You don't see that the assertion has been failed. Okay, so if you see here at 14 nanoseconds, it is not failed. Okay, at 18 nanoseconds, the assertion is being failed. Okay, so in this way, depending upon the time units that you observe, you can just check at that particular time in the in the waveform, so that you will get the place where the assertion or the logic has actually failed. You have already seen this implication operator while we are talking about the OOPS concepts. So, yes, implication operator is basically denoted by this symbol. A dash and arrow is just like an arrow symbol. Okay, so in system Verilog assertions, you are having two types of implications. One is overlapped implication, another one is non-overlapped implication. So, what is the difference between this overlapped and non-overlapped implication? We are going to see this today in detail. So, for example, if this is a sequence, as if you see, this is the sequence A hash hash to B. So, what is the meaning of this is after A is high, then after 2 clock cycles of time, B should be high. So, this is the meaning of this particular sequence. For every passage of clock, after A is high, then after 2 clock cycles, B should be high. So, this is my condition for this particular two signals. Now, if you are writing only one sequence, then it is fine. Similarly, if you are writing some 2 or 3 sequences, and now you should know which sequence to be executed first and that means which sequence condition should be checked first and which sequence condition should be checked next. So in this way, if you want to follow the order for your sequences, then it is possible by using the implication operator. Okay, so in implication operator, basically just like implication operator is very similar to this particular logical operators and all. Okay, so similarly, just like you are having two input signals A and B, similarly in implication operator also you are having two signals. So the left hand side signal is called antecedent and the right hand side signal is called consequent. So basically the left hand side signal will be executed first. So after the left hand side signal is executed, then only the right hand side signal will be executed. So basically after this happens, then this happens. So that is the meaning of this arrow signal. That means after antecedent execution, that means after checking the antecedent signals, then the consequent signal takes place. That means then this is evaluated. First, the evaluation is done on antecedent, and then the consequent evaluation will be done. So, this is the meaning of this implication operator, right? So, basically, here you are having again in this, like if you see here, within this evaluation, like antecedent and after consequent, also you are having two kinds, like overlapped implication and non overlapped implication. Basically, the overlapped implication and non-overlap, how can you detect the difference between these two things is by using the symbol. Okay, and also one important thing that you should remember is this implication constructed can only be used in the property definitions only. You can't use this in the sequences. You can just use this implication operator in the property itself. So let us see what is this overlapped and non-overlapped. So basically, overlapped is denoted by this symbol. Okay, so dash and this one. Okay, but non-overlapped means it will be in this way. So double equal to symbol with an arrow. Okay, so this is, don't get confused, this is non-overlapped and this is overlapped. So let us see now what is the difference between this overlapped and non-overlapped. Okay, you can just pause this video and just study this, but I want to give you an example for this in a picture format so that you can easily remember it very easily. So let us see this particular property. So in this property, for every positive edge of the clock, so what is the property? Valid. So this is my antecedent, and this is the equation A hash 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 double hash 3 and B. So this is my consequent, and if you see here, this is the implication operator. So what you know according to implication operator, after antecedent is evaluated, then the consequent should be evaluated. So this is fine, right? Now, if you see this, this is the if you see this, this is the overlapped implicator. So what it should happen means for every passage of clock, the checking will be done, right? For every passage of clock, after valid is 1. That means after valid is high, in the same clock cycle, this consequent should also happen. That means if you see here in this clock cycle, in the first clock cycle, valid is low. So assertion is failed. And in the second clock cycle, valid is high. So as soon as the valid is high, within the same clock cycle, the particular consequent logic like A star B, this also should be high. That means A should be high. And after A is high, according to this logic, after A is high, after 3 clock cycles, B should be high. So after 3 clock cycles, B will be high. Clear? So in this way, within the same clock cycle, both antecedent and consequent should happen. Okay, so this is the overlapped implication. That means one assertion is overlapped, antecedent is overlapped on consequent. So clear? So this is about the overlap. The entire opposite is non-overlap. So what is the overlap? Actually, you have seen. Now, if you see the same condition, but this is the non-overlapped assertion. So what happens here? After at the first clock cycle, valid is 0, so assertion is failed. In the second clock cycle, the valid is high. So since the valid is high, then the second equation, that means A should be high after the next clock cycle of valid. That means in the first clock cycle, if valid is high, then in the next clock cycle, A should be high. Okay. Then after this, after 3 clock cycles, the particular B should be high. Clear? So in this way, this is non-overlapped. That means after first antecedent happened, after first antecedent is evaluated, then in the next clock cycle, the next consequence should happen. Okay, so this is the non-overlapped implication operator. So basically, you are having two implication operators, which is overlapped and non-overlapped. So you have to check while you are writing if there are conditions. For example, if you were asked to write a condition where as soon as the antecedent, like if in the property, if you are asked to check whether two sequences are happening at the same time, or whether after first sequence is happening then the second sequence should happen, if you are given a condition like that, so by using this overlapped and non-overlapped implication operators, you can check it very easily. You can write the assertion very easily by using these implication operators. Clear? Hope you got an idea on what is implication and non-implication operator in the property. Again, in this implication and non-implication operators also, just in the previous session we have discussed how we will be inserting the delays within the sequences. Just like that, within this particular implication operators in the property also, you can insert the delays. Because if you see here in the now you may get a doubt that since if we can use this non-implication operator like non-overlapped operator, the delay will be happening. Yes, the delay will be happening, but it is only for one clock cycle of delay. Yes, is it or not? But if you want the second consequent to evaluate after some particular period of time, after some clock cycles, then you should insert the delays. Okay. So, for example, if you see this operator A overlapped implication B and you are giving the delay. If you have not given this delay, then what happens? Within the same passage of clock, after A is high, then immediately B will be high. But you don't want that condition to happen. What is the thing that you want to check? After A is high, then after 2 clock cycles, B should be high. So now what happens? Instead of using instead of writing it just using, if you are using the non-overlapped operator, only one clock cycle will be delayed. But if you want more number of clock cycles for your B condition to be applied, then you can just use this hash hash 2. This is the, you already know that this hash hash is related to delays. I have already explained it clearly in the previous session while we are discussing about the concurrent assertions. As I told you, I'll link that in the description box. You can go there and check it out. So the same thing, this is how you will be writing by using the implication operator within the properties. But if you are writing within the sequence, you can just write it as A hash hash to B. Okay, so this is how you will be writing your sequence and properties. Now let us see how we are going to use it actually in real time while you are writing the codes within the developing the codes in test wins. Okay, for example, these are the two sequences I am writing. So this is my sequence 1 where the logic is A and B hash hash 1 C. That means after this logic is happened, then after one clock cycle of delay, then C should happen. C signal should takes place. Then within the sequence 2, what I am writing after C, that means after this particular sequence or this particular sequence is based on the property. So here actually according to property, first sequence 1 should happen, then sequence 2 should happen. Now that means after A is 1, then B should be 1 because both should be 1. After these A and B are high, then only C should be high. That means after A and B both are in high condition, then after one clock cycle, C should be high. Okay. So for example, if it is at one clock cycle, then after 1 plus 1, 2 clock cycles, this C should be high. Okay. So this is the condition. Now after this, that means after C is high, after this sequence is happened, then the second sequence should be evaluated. So what is the second sequence? After C is high. So if you see here, I didn't have any other condition. I have just mentioned the delay and not of 2. That means after C is high, then after 2 clock cycles of time, what should be? D should be not high, but it is not D. So D should be 0. So this is the condition I want. That means I want it as 1, 1 and 1 and 0. So this is my condition. That means A and B both should be high. Then after one clock cycle of delay, C should be high. Then after two clock cycles of delay, D should be 0. So this is my condition. So I have inserted everything within the two sequences. And now what I am doing, I am writing the property where for every passage of clock, what I am doing, I am just checking these two sequences. So since this is an implication operator, that two overlapped implication operator, then what happens? Sequence 1, as soon as the sequence 1, that means as soon as A and B hash hash 1 C happens, then in that case immediately the next one, if since I have given delay here for 2 time units, so after C is high, after 2 clock cycles, D will be 0. But if I didn't mention any of this delay, then what happens? As soon as the C is high, in that same clock cycle, the D will also be 0. Okay, so this is the implication operator. Clear? So this is how you will be writing the implication operators within the, this is how you will be writing the assertions within your system Verilog codes while you are developing the test benches. Okay, so similarly, just like you have used the time delays within the sequences, you will be using the same within this particular properties also. If you see here, it is within the range. That means after A is high, then within 1 to 4 clock cycles, B should be high. Okay, here everything is same because if you see here, mostly the time delays is everything same. But here, if you see, this is the range. That means within 1 to 4, B should be high. And here, if you see, this is the it should be between A should be high on given passage, then B is high in the same clock cycle or within 4 clock cycles. Because here I have mentioned it as 0 to 4, so it is either within that clock cycle or from 1 to 4 within any of the 4 clock cycles, the B will be high. Okay. Now, if I am not mentioning it is anything like if you see here 1 to dollar, so dollar denotes that until and unless there is like until and unless this simulation is happening at any point of time after A is high, the B can be high. If at any point of time if B is high, after as soon as the A is high, then immediately you can say it as an assertion. The assertion has passed. Okay, if you don't want to give any time limit for the another sequence, then you can be writing it in this manner. Okay. Now the same thing for repetition. We have seen this repetition operators within the sequences also. The same goes with this properties also. I don't want to repeat again. So this is all about assertions in system Verilog, and hope you liked it. Hope it is helpful for you. If you like it, please give it a like and also share it to all the VLSA aspirants.